Hi. In this video, we're going to be looking at how we can use the Python programming language to help visualize the one-dimensional wave equation. So, as an undergraduate engineer or physicist, you'll probably come across the wave equation at some point. And the wave equation basically relates how the displacement of a wave, so for example, if this was a wave on a string, the wave equation is describing how the displacement along the string is a function of both the time and spatial position. And it's a partial differential equation, which means that the curvature in space is related to its curvature in time. So what does that mean? It means that where you have a large curvature along the string, so for example here, once it comes back around, you will then have a large change in its curvature in time. So it's more likely to change in time, or another way of putting it, it experiences a larger change in time at that particular point because its curvature is so great. Whereas at places like here, here, and here, where the curvature, remember curvature is the second differential, is zero, so it's not actually experiencing any displacement in time. So you see it remains along this center point. And so that's quite important. And once we put this model into Python and use Python to actually simulate how the wave on the string behaves, we can actually start putting in more interesting scenarios. So for example, if I run this, we can see that if you were to pluck a string, for example, so hold it up at one end and then release it, you see the wave travels in a way you might not think it would. So this is always quite interesting. You see how the initial shape of the wave just simply bounces backwards and forwards along the string, which is quite nice. And this may seem, oh, well, this can't be right. This doesn't look right at all. But if I play this video, which is a video of a guitar string being plucked, you can see that when the string is released, the wave maintains roughly the same shape, and then it moves along to the end of the string, and then it reflects at the end point, and then comes back in the same shape. And this goes on over and over again because the guitar string is quite stiff. That's a really nice video showing how we can actually simulate real things. So it's using a programming language, putting in some physical laws, and actually being able to simulate what actually happens in real life. So I think that's really nice. If I close that down, we can go ahead and start coding. First thing we need to do is we need to try and figure out how we're actually going to solve this. Typically, a computer program cannot solve a partial differential equation. So, well, I mean, it can, but then we get analytical results, but we're going to want numerical results because we're going to want to potentially put in some quite crazy initial conditions that aren't necessarily nice mathematical functions. So in order to do that, we need to use another resource. So what we can do, so if I go on this SEG wiki, there is a page for solving the wave equation in one day, which is always very nice. And so it takes the wave equation in one dimension, and then scroll down, and we see that there is an approximation to this equation, so a way of solving it, which uses the difference equation. So basically what this equation does is it breaks up the string spatially. So rather than it being a continuous object, it actually breaks it up into small chunks. So for example, if the string is 100 centimeters long, when modeling it, we might break it up into 1 centimeter chunks and model each one of those as a straight line connecting all the different nodes, so 100 different nodes across the string. And likewise, it also breaks it up in time. So rather than being continuous in time, so from going from say 0 seconds to 1 second smoothly, what we do is we break it up. So we might say that, okay, I want to know what happens 1 millisecond from now, so 1,000th of a second from now. And then we're going to simulate that. And then we say what happens 2,000ths of a second from then. and then keep adding on 1,000th of a second until we get to that 1 second. So we're discretizing in both space and time. And it's an interesting read. I'll link this page in the description. But basically, at the end, you come to a formula called the recursion formula, which, if I zoom in, we can see that what it's saying is the index j is the spatial index. So this is saying whether the point is, so whereabouts in the string you actually are, so physically, so that's your x coordinate basically, or x index. And then the I is the temporal index, so that's saying that whether you're here in time, you're back in time, which would be I-1, or you're forward in time, which is I+1. So it's saying that along the string, pick any point, which is given by j, and its next displacement, so where it's going to be, is related to where it previously was. So where it was just a short time ago, where it is now, and also where its neighbours are. So it relates everything about it. So it's this weighted sum of where it is, what its neighbours are doing, and where it was. So all of these come together to create this recursion formula. And this recursion formula, as the name would suggest, is recursive. So we can use this formula over and over again to actually build how the string evolves in time. And so we're going to be putting that in our little piece of code. So I'll keep this tab open, and then we can start coding. If I bring that over here, shrink myself there. So the first thing we're going to want to do, so I'm using Spider. So Spider comes with the Anaconda Python package library that you can download, and that's quite common for people in data science and undergraduates in particular, probably downloading Anaconda, and Spider's probably the first IDE you'll get to use. So I'll be using Spider throughout. I do a little zoom in there. I'm going to start coding. Let's write our equation at the top, because we want to continually know what we're actually trying to do. Don't ever lose sight of what you want to do. So we're trying to solve this equation. So the rate of change of y with respect to time, so the second order rate of change of y with respect to time is equal to this constant c squared times the second order change with respect to y over space. So that's the equation we're trying to solve. And like most things in data science and doing things like this, probably almost always going to want to use NumPy. So that's numerical Python, contains all the nice library functions you'll need for doing math. Let's have a think. So what do we actually need? I'm a big fan of object-oriented programming, so you could do this in just one big script, lots of for loops. But I always think, give me an object. So we're obviously going to be trying to simulate a string, for example. So a string, and a string is an object. I can hold a string, I can pick it up, I can do things with it, I can try and oscillate it. Okay, and because a string is an object, that means I'm probably going to be using object-oriented programming. Let's go ahead and create an object class called string. And the good thing about Python is that the native string class, so for typing out words, etc., is actually str, so you can actually use string, which is quite nice. Okay, so we're going to create an object called string, and now we need to think, what does the string have? So what properties do we, or in the context of what we're trying to do, what properties does the string have? So let's create the initializer. So this is the code that is run when you create an object of class string, self, and we have to think this string is going to be characterized by its x coordinate. So the string has a length, but also has to be discretized. Call that x. It's also characterized by an initial state. If I have a string like this, it can have many different initial states, so many different shapes. And we also need c. So if you look in this form at the top here, we have the variable c, which is its wave speed. Okay, and then we need to think, well, what do we need to do? So when we create this string object, we're going to want to know, we're going to want to actually keep these values in there. Let's do self.y. Self means within this instance of the class of string, keep this keep this variable. So we actually create a variable within the class itself called y, which means it's accessible from any other method. So self.y, and then we're going to say that self dot, no we're not, we're going to say that that's just equal to y naught. But I'm going to do something a bit different. I'm going to do numpy.copy, because if I just do self.y equals y naught, I'm going to actually take a reference to that object to y naught. So if I changed y naught or x outside of the class, then it's going to change inside the class as well, and that's not desired behavior, because remember this y is the displacement of the string, so we can think of that as the current state of the string. And as that changes, we want the string object itself to know that it's changed its own state. We don't want some outside force to be able to just change it arbitrarily, some outside influence. Okay, I'm also going to have self.x, because we want a copy of the actual x coordinate. So this is the discretization in space. Okay, so they're the two things. They're the two things that are going to keep track of the actual state of this string. We will need one more thing though, however, in that it would be useful for us to have a reference to the initial state of the string, and I'll explain that a bit later, but it's going to relate to the boundary conditions of the string. So numpy.copy. And we'll have another copy of y naught. So both these are now independent, because obviously we're going to be changing y. We'd ideally want y naught to be the same, and we don't want any of these to change when the original array that was used to construct these is modified. That's the three things we want there. And we also want a copy of this c, self.c. And for now, just put a c, because that should just be a value. That's that. Now there is one thing that we need to quickly note, that if I go back to the recursion formula, we can see that in this formula we have obviously the current state of the string, so its current shape, and its previous shape, so in time, that's fine. But then we also have this section here, which is saying that look to its neighbour to the right. So if you have a point on the string, so here in the middle, it's going to say, well, what's the point to the right of it doing? Okay, that's fine. But then what's going to happen at the end of the string? The string is clamped at the end, but then I need to look at the neighbour on the right to see what's happening. When we go ahead to actually simulate this, you can do a few different if statements that basically say, if you're at the end, do this instead of this. And what you end up with is like a lot of different if statements to handle all these edge cases. So you end up having to type this formula out several times with some different conditions due to these end pieces. But what's quite common when solving these finite difference equations is to say, well, actually, why don't we just pad the string? So rather than say the string has an end that's clamped, why don't we say it's got an end that's clamped and then a point next to it that's also clamped? And this point here that's clamped at the very end, so this extra clamped point will just be a copy of this point here. So that when we go to solve this equation, we can just say, well, actually, let's just focus on everything but the very ends. We imagine that we're now, rather than being clamped here at the end of the string, we have a little extra bit that's clamped. And then we say, well, just solve the actual main piece of the string, like the displacement of the main piece of the string. But then we can use these points when needed. And remember, these are just a copy of what's already at the end. What we can do for that, let's create a little function called pad array. Pad array. And it's going to take something called array. If you don't know what self is, by the way, self is every function in a class if it's past self, or every function in a class when it's called, it will always be called with a default argument, which is the actual object itself. So this will receive, so this function here is basically receiving the class itself. That's what's called self. And then this allows you to access any other part of anything within the class by just typing self. So for example, this pad array now has access to y because I can just do self.y. Because remember, self is class string. We've already said that within string, there exists a variable called y. That's what that is, if anyone's wondering. And what we can do here is return concatenate. Let's concatenate, so that means just put these things together. We're going to put the array, the first element of the array. So the reason I'm doing this instead of this is that when you just put the 0th element of the array, so the first element of the array, the 0th element, when you put that, it will return a number. So let's just numpy dot, let's actually show what I'm doing here. So if I have an array, sorry, let's do 0, 1, 2, 3, 4, and then I do all that a. Let's do a of 0 will return a number, and concatenate will throw an error saying it's not an array. I can't concatenate a number to an array. It doesn't actually make sense. But when you do this instead, you see it still returns the first element, but then now the first element is an array, and arrays can be concatenated. So that's what that is. And then we're going to do the array itself, and then we're going to do the array to the end. So in Python, you can negative index, so -1 means the first element from the end of the matrix. Basically, you can wrap around. And what does that do? Let's actually just copy this over just to show what it's doing. Where the original array here is 0, 1, 2, 3, 4. This one is 0, 0, 1, 2, 3, 4, 4. So all it's done is add the end elements of the element from the start of the array and the element to the end of the array onto the start of the array and the end of the array. So it's padding it with the value that's already at the end. That's why it's called pad array. We're going to take this pad array function. We're going to ignore the copy now because the copy itself is not needed, because this function here creates new arrays, because this concatenate will return a new array. So we're going to pad array instead of copy. Let's just go ahead. Pad. Each one of these returns something new. Okay, so each one of these now, so x, y naught, for example. Let's do self, because it needs to know that this is a method within the class. Should work. There we are. So now internally, these variables y and y naught have been padded. We don't actually need to pad x. So y and y naught are padded arrays. The arrays will actually be slightly longer. For example, if we do 100 elements to represent the string, then the array y and y naught will actually be 102 elements. So 1 bit at each end. Then what we need now is we need a way to increment it. We spatially segregated the string, chopped it up into loads of little bits in space. What we need to do now is say, well, we need a way to increment that in time. And then we're actually going to give it a DT. I'm just going to write a quick description. Increment shape of string by DT. Basically saying solve for the next value of time. Okay, so to do that, we know that the next value of the shape of the string, so y, is equal to twice the current value minus the previous value in time, plus this factor r, which is given by this, times everything to the right at the current point in time, minus twice everything now at this point in time, plus 1 of everything to the left at this point in time. These terms here, this ji, anything with I at the top is basically just self.y, so it's the current state of the string. Anything with I plus 1 is the new state of the string, and anything with I minus 1 is the previous state of the string. If we go ahead and think about that, we're basically saying, let's call it y next, so the next value in time of the string, okay? The next value of y is equal to twice the current value. It's going to be 2 times, remember, self.y. Remember that we're only interested in the middle section. We're not interested in those extra 2 bits at the end. Those extra bits at the end are only going to be used when we come to these bits in the formula. So actually, we're going to choose everything but the very end pieces of this array. Remember, if this array is 100 elements, if this original array was 100 elements long, then this self.y is 102 because we padded it. Basically taking the middle 100, ignoring those very 2 endpoints. We're going to take off the previous value, self dot, but the thing is we've got no indication what the previous value was. I mean, at first it's going to be just y naught, but going forward we do need a way of actually saying, well, what was the previous value of y? Let's call it y underscore previous. And then let's quickly go back. We can say self dot y underscore previous is just equal to numpy.copy. So let's make a copy, because remember we don't want anything we do to y to affect y previous. Let's say it's numpy.copy, and let's make a copy of self.y. Doesn't actually matter at this point because they're all the same. So now we have a previous value in time, and again we're going to choose the middle bit, middle chunk. Then we need to add this value of r, so let's call that r. Let's actually work out r here. So r is equal to, and the interesting thing about r here, obviously we have self.c, we have access to c. We need to change it by dt, okay, that's fine. Then we need to divide by dx, so that does require if it's a constant, it would be basically saying that the spacing between the points on the string, so if we split the string up into 100 points, that's 100 equal spacings. Now we don't actually need it to be 100 equal spacings. What we could do is, rather than just write the spacing between the elements on the x, basically, we could do something like numpy.gradient of x, which then will return an array. So this r will then be an array of length. Let's go with 100. Can be used. So if we did have unequal spacings, it would actually work. So we'll put that in, even though we probably are going to be making constant spacings when we discretize our string. And then in this bracket here, so this is the interesting part, is we need to say everything to the right. So it's basically saying, if you're at point 1, you need to look at what's happening at point 2, and also you need to look at what's happening at point 0. So the index of the array. Every point to the right would be self.y. Remember, this is also in the current point of time. And we're going to do 2 to the end. And that's because, remember, we're not interested in what's happening at the very... we're interested in what's happening at the very left end when we shift it right. But also we've added 2 elements to the matrix, so we need to go 2 over. And then we need to do minus twice what's happening now. So self.y. And again, 1 to minus 1 plus self.y. Move this over. Everything shifted to the left. So that's start at the very left index and then only go up 100 points and ignore the last 2. So that should be everything required. But now we need to think what's actually going to happen. So this y next will be created. So Python's loosely typed, so you don't need to declare variables beforehand. But this here is going to have a length that's wrong for what we need. We need to think, what do we actually want from this? Really, y next is going to become y on the next iteration, and y will become y previous on the next iteration. So what we really need to say is, well, actually, when we come into this loop, let's create a copy of the current state of the string, self.y. And then what we're going to do with that is say that when this little calculation's finished, is that the previous value of y will become this. So now we have a copy of y, so we don't actually need to preserve the state of y anymore. So what we can say is self.y. Okay, and remember, where this equation here will only return the middle. It's only operating on it's only operating on 100 values out of the 102 that the array might be. So what we can say is, well, actually, everything, only the middle part of this array you're going to operate on. So then the 2 end pieces become the same. And then we say self.y previous, and the previous version of y now equal to temp. Remember, temp is a copy of what y was before it was changed. That should work there. And then we need to be careful. So we need to think about boundary conditions. We're going to put some hard boundary conditions in here at the minute. When we do our string, we're going to clamp it at the ends. We're going to take a string and clamp it at the 2 ends. Okay. And Now obviously this equation has worked on the inner 100 points of the string, which includes the original clamps, and we don't want those to change. They need to be the same, so that string needs to be clamped back how it was. So what we're going to do is just ensure that everything is clamped. We're going to say, even though the endpoints may have changed, manually override those points that have changed back to how they were when we originally received the array. That's why we saved this y0 here. We basically said this was the original state of the array when we received it, so the initial shape of the string. Now clamp the end points of the string, which is basically the 1 and -2 index, to how they were originally, and also just ensure that 0 and 1 index are also clamped. And actually, thinking about it, the 0 and -1 index won't actually change, so they'll always remain at 0 because they're never actually modified in here. So you can get rid of this 0 and -1, but you still need the 1 and -2. But that should be it for actually being able to increment the shape of the string in time. So we're going to go ahead now and actually show that we can change the string. Let's just quickly write in some parameters. So I'll just copy and paste some over, but basically we're going to have an initial displacement of the string and where that displacement occurs, and all will be revealed shortly. We're going to have an initial speed of the string, so this constant c, and then we're going to have, say, okay, we're going to have a string that goes from 0 to 100 in 128 steps. That's just a nice power of 2. And then we're going to create an empty array, so we don't need to initialize it to 0 because we're going to be changing the values. We want it to be the same length as x. And then let's go ahead and say that will become clear very shortly. Right, let's go ahead and plot that. So almost certainly as an undergraduate, you'll be using matplotlib for most of your plots. They create nice pretty plots. Insert, and let's create a quick figure plt.subplots. And do x.plot, and then we want to plot x and y, see if it works, and it does. So the string goes from 0 to 100, and its displacement is given by this d0 here, and the actual point at which it is displaced is 80% along the length of the string. So here, you see it's 80, it's been plucked up basically. So this is a plucked string, which is the same as the guitar we saw at the beginning of the video. We've now got a situation where we've basically plucked our string and this is its initial shape. Now if we simply create a string object, so let's say string, and again remember Python, the native string object is called str, so we can actually use the word string, which is very nice. So string, we're going to give it a x, y and c. X is here, y is here, c is here. To run that, no errors, good. And then we're going to increment it, string.increment. Let's try 1 e to the -2. So we're going to increment it by 1/100th of a second. And then we're going to do the same thing. We're going to plot this, but we're not going to plot the original x and y. We can plot the original x because that's not actually changed, but we need to actually extract the variables from the string, so string.x, and we can also do string.y, but remember string.y is 2 elements too big, so if I just is string.y, you'll see I get an error, not that error. Now there are look, x and y must have the same first dimensions but have shapes of 128 and 130 because string.y is 2 elements too big. It's got an extra bit at the front, an extra bit at the back. Easily solved by just indexing the middle portion. Plot that, let's have a look. Okay, so it definitely plotted something over that, but it just might not be enough time for us to be able to distinguish between the two. Let's go ahead and do 1/10 of a second. Run that. Oh, look at this. Something did happen. After 1/10 of a second, the string has moved. And let's just do something a bit bigger. I expect this not to work. You see, now we have a problem. For some reason, when trying to do a full second increment, it's not worked. So there's something called the CFL condition, which basically says that in order for stability, so when you're solving these methods, you need to ensure that your time step is not too big. If your time step is too big, then you're going to run into stability problems. So what we need to do is we need to ensure this condition is met. So if we go back now and have a look, we can put this in. let's just quickly go back to what that was. So it's delta x over c. So if we get our delta x, because we know this is spaced equally, we'll just do, I suppose, the average. So we can say the last value of x minus the first value of x divided by the length of x. And that's basically the step of x, the average step. And then we look back here. If we look now, dt, saying that we can step 0.078 seconds at a time without it being unstable. Let's turn that to twice. So you can see now we start getting some horrible stability issues. It's like it's working, but we can always change that later. So let's keep that. Let's put that to half of this LCS condition. And then again, yeah, we'll increment there. Let's just do this 10 times. There we are. So it looks like it's working. So each time step we take, this dt, it looks like the shape of the curve, shape of the string is changing, which is awesome. So I think I'll leave this video here because it's gotten quite long already. In the next video, what we'll do is we'll take this string simulation basically, and we'll keep iterating through it, and we'll try and plot it in real time. And so we'll see what actually happens when we plot this string over time with a sensible time step, see how the string evolves. And as we see, like that guitar video, that's exactly what we should see. So yeah, I mean, stay tuned for that if you're interested. Thank you very much.